Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video, we're going to be looking at Chapter 2, which is the physical properties of pure compounds. And in this video, we're going to be looking specifically at graphical representations of properties. Now, you'll recall that we're going to be defining a state in terms of those physical properties. And so we want to do a little bit of a deeper dive. Now, the large diagram you see here is for pure carbon dioxide, and the smaller one is for water. And we'll talk about the differences between those in a few moments. Now, first, I want to point out to you that what we see is we have pressure across the vertical axis, and the horizontal axis is temperature. And that's going to be really important because we want to be able to talk about what happens as things change temperature or change pressure. So if you see, we've got over here in the colder temperatures and the higher pressures, we have solid form of CO2. We would call that dry ice. If we go to the higher temperatures and pressures, we're going to see gas form of CO2, which is what I think most of us typically think of CO2 as. And then we can actually get a liquid at higher pressures and higher temperatures. Okay. Now there are lines that separate out these regions of solid, liquid, and gas. And then there are a point at the where they all intersect and a point up at the top. Let's talk specifically about those points first. Now, this point right here is the triple point. So we will frequently designate this with a TP because, again, an engineer may be a little bit lazy from time to time, and so an abbreviation is helpful. So the triple point is a unique point for a pure substance where the solid, the liquid, and the gas can all coexist at one point in time. And the key thing is that it is a point. There is a particular pressure and a particular temperature where this can occur. No place else. The curve that is going between, that separates the solid and the liquid, this is going to be called the fusion curve. Okay. We also could call it a melting point, but this is where the solid goes to liquid or liquid goes to solid. So freezing or melting, okay? And that's fusion. This curve, the lower pressures and temperatures that separate the solid and the gas, those are the sublimation curve. On a very cold day, you may notice that the ice if you get up really early, sometimes you can see kind of like little wavy lines coming up from a very cold surface where the frozen solid snow or ice or whatever is actually converting into a gas, and you can see that happen. The one we're probably most concerned with, in our everyday life is vaporization, and that is where liquids and gases are in equilibrium with each other. So a liquid vaporizes to become a gas, or a gas is going to condense to form that liquid. Now we have one last point of interest, and that is up here at the top of this vaporization curve. That is called the critical point, okay? Beyond the critical point, you no longer have a clear liquid and gas phase separation. This is also because it is a point, is it a unique temperature and pressure that's identifiable for a pure substance. And anything beyond this is called a supercritical fluid, all right? Means that it flows. It's going to be sort of gas-like, sort of liquid-like. A little hard to say, so we just call it a fluid, okay? Now, we also Okay, I want to talk about the differences between these two graphs. All right, we have a graph for CO2 and a graph for water. This is typical of most pure substances. All right, there are only one or two substances, water is the only common one, that have a graph that looks like this. Now, what's the difference between them? Sure, it's a little stretched up higher, right? The triple point is at a higher temperature and higher pressure. All right, the critical point is at a different location. That's going to be true of any substance. They're always going to have a different triple point and critical point, but the shapes of the curves will be pretty much the same. The difference is in the fusion curve. This line right here, okay? Compare it to this line here. Normally, they slant off and are going to be a function with a positive slope. But for water, it's unique. It has a negative slope. That actually is going to be very significant in terms of a lot of processes. But mostly it's going to, like if you take biology, pay attention because that's going to make a lot of things possible that wouldn't be possible otherwise. So water is very unique, but one of the key things that we can see already is the shape or the slope of its fusion curve. Now we want to look. These three graphs can be combined, right? They have common variables into a single three-dimensional graph, pressure versus volume versus temperature. And this is a representation of that, and you can look in your textbook for some others that may be more useful to you. Some people find these incredibly helpful. They really help them cement in what they've been learning, and other people just find them stressful. So you make the choice whether you want to spend any time studying this diagram or not. Don't worry, I will never quiz you over this particular diagram. So this is an overview of our three basic diagrams that we're going to see for properties. And we're going to talk about other properties and how they may be represented graphically in our next lesson. Thank you very much for your time.